Hello, Eric and I, Jay, will be talking about our mini project from assignment 2.
For our project, our research questions are: how can we model the spread of disease through a forest, and does the type of forest matter? We aim to answer these questions using cellular automata to model spatial dynamics.
We chose a three-state system where each individual in the population can be in one of three states: susceptible, infectious, and immune. The goal is to observe how the disease spreads over time and what the effects of immunity might be on the overall tree population dynamics in the forest.
Our rule set is simple. If a susceptible tree is next to an infectious tree, the susceptible tree becomes infected.
And in our model, we use the von Neumann neighborhood to update the state of each tree in the grid. So this defines each cell's neighbors as the ones directly to its left, right, above, and below.
We first start by setting the initial conditions by defining the matrix size, forest type, and the distributions of susceptible and immune trees, along with the initial number of infectious trees. We then generate a forest, given our three types of forest, and then we simulate the disease spread, running the simulation to observe the infection process.
We experimented with three conditions. First, we generate a randomized grid where the trees are randomly assigned one of three states: susceptible, infected, or immune. This grid represents a forest where trees are scattered randomly and their health status is determined by specific percentage we predefined. Second, we have the checkerboard grid. Instead of assigning tree status randomly, this method organizes the tree into square blocks where each block contains only one type of tree, and this grid is more structured and represents a forest where different regions or patches have distinct health conditions. However, some research have shown that in nature forests, trees are often distributed in cluster, or what we call aggregate distribution, to simulate this clustering effect. We first start by randomly selecting a center point in the grid. From this point, we randomly select a tree type. Next, we calculate the distance from the center point to every other cell in the grid. And we then use the distance to calculate the probability of assigning a tree type to each cell. So the closer a cell to the center, the more likely it is to have the same tree type as the center. So this process is repeated several times to create multiple clusters across the grid. Finally, any remaining cells that are not assigned will be filled randomly.
Our initial hypothesis is that an increase in tree clusters will lead to more infections in the forest. This is based on the idea that disease spread is more destructive in monocrops. Therefore, we hypothesize that a fully randomized forest would be more resistant to the spread of disease. In our model, this hypothesis appears correct. After running multiple trials for each forest type and varying the proportion of susceptible trees, we found that the random forest had fewer total infections on average and fewer extreme outliers. The Jackson Pollock forest ranked second, followed by the checkerboard forest. This pattern held at all susceptibility levels: 10%, 20%, 30%, 40%, and 50%. At 50% susceptibility, roughly 10% of susceptible trees, on average, became infected in a random forest, with the highest outlier around 30%. In contrast, the checkerboard forest saw an average of 48% infections, with the highest outlier of nearly 100% of all susceptible trees becoming infected. The Jackson Pollock forest average was between these two. On average, the Jackson Pollock forest infected 38% of susceptible trees, with the highest outlier of around 50%, which is right between our randomized forest and our checkerboard forest. During the early to mid 20th century, American chestnut trees were devastated by chestnut blight, a fungal disease that came from Japanese chestnut trees that were introduced into North America from Japan. It is estimated that the blight killed between 3 and 4 billion American chestnut trees in the first half of the 20th century. When hearing news of the blight, many people panicked and started an effort of mass timbering and burning of the American chestnut. The idea being to thin the trees out so the blight wouldn't spread as fast. However, their system was incorrect, and the blight spread through carrier trees as well, which only caused the tree's destruction to occur faster. Using modeling techniques of today, it's possible the near extinction level event could have been mitigated, and the range of the aptly named Sequoia of the East would still remain to this day. Thank you for watching.